Okay, so we can continue with Hernán González talking about scalar subleading expansion from infinite tower of conserved charges. Please go.
Thank you, Andrea, and thank you for attending my talk. It's been a very nice workshop so far. I have learned a lot of new things. So today I would like to explain my recent work on expansions in the energy in a very simple example of scalar field theories, and how this expansion arises from an infinite tower of conserved charges at each order in omega, in the frequency, okay? So this is a work in collaboration with a PhD student, Matías Briceño, Mar Genó, and Alfredo Pérez. Also, we have something, so this work in progress is like something that I might be talking at the end of the presentation, but the work will be based on this archive number 2504086112. Okay, good. So this is the plan of what I would like to present. So please interrupt me at any time if you have questions. So first, I will give a brief motivation of why I'm interested in this subject. Also explain why scalars. So they seem a bit weird from the perspective of gauge theories, but as Robert Wald was mentioning, whenever you have a massless field, you will have memories in his case, but also like, as I'm gonna show, there will be a soft factor appearing. Then I will discuss how you construct these conserved charges and how do they lead, how those charges lead to Ward identities. And then I will see that there is a consistency with the perturbative analysis. And at the end, I will present a summary and some challenges that still remain. Okay, good. So yeah, so as we have seen in this workshop, soft theorems have shown a deep connection with asymptotic symmetries. Also, they have asymptotic symmetries have allowed us to understand better radiation and also to give a better understanding of holography in flat space. So the basic tool is that for gauge theories, you construct codimension 2 surface integrals that are conserved, and they generate a transformation of massless fields. Here, I'm particularly talking about the case of asymptotically flat spacetime. See? So this is has been a very old work ever since BMS started in the 62, and it has been refined by Reggie Teitelboim, Walt Supas, Varnich Brandt, and many others who have been working on this thing. Also, I have to mention that all this idea of relating this setup with holography has also has been because of like the great work of Brown and Heno. So yeah, perfect. So then here the idea is that large gauge transformations that describe plasma are symmetries of the metrics, and this implies or like is equivalent to the leadings of theorem. Yeah? So the leadings of theorem of Lowe and Weinberg. And there has been like many works on this idea. Everything has started from the work of Strominger, who realized this connection. And then there has been connections to, of course, subleading corrections in gravity, in QED, and Yang-Mills. So all theories with massless states. Okay, good. So then there is this very nice article. Divecchia, Nolli, and Bern have shown that some contributions of the amplitude of the soft, taking the soft limit of the amplitude, are related to universal soft factors. So in QED, for instance, it's with this one. I just want to calibrate the pointer. There. So in QED, the first two contributions, the Weinberg soft and the subleading Lowe theorem, are the ones that are universal. And then in gravity, you also have three more that are also related to the linearized diffeomorphism invariance. So those are considered universal. So They in some way are considered like theorems in the expansion of the energy. But it has been shown by Hamada and Xu and Lilin and Zhang that also there are plenty of non-universal subleading factors. And the difference here is that they depend on the nature of the interaction of the particles. So for instance, here I'm just quoting the case of when you have an amplitude or a process that interacts with, well, Maxwell with the scalars and Maxwell with gravity. So you get one part of the amplitude, this is a tree level, of course. You can show that it factorizes, and this factor adds an infinite tower of these guys. So here you get, like, in QED is this subleading factor, and then for the next orders, you start getting this differential operator to the power L. So each order you go in the energy appears one more operator in this Q times dk. And for gravity, it's the same, but with one order less. Okay? So, good. So these are, of course, non-universal because they depend on the interaction of the particles. Yes?
Subfactoring gravity is non-universal. I remember this fact. So that, I mean, when you have, like, you know, electromagnetic field, but interacting with other fields, S0 can be modified and S1 in gravity can be modified. Just to...
Yeah, that could be true. I mean, I'm just saying that here that gauge symmetry fixes this form of the subfactor. Maybe that one can be corrected, yeah. But
yeah, but this is what I'm asking. In what sense are you saying it's universal if it's theory dependent? Yeah,
what I mean is that I'm just from this that is related to gauge invariance. This is, I mean, can be modified, but this part is related to gauge invariance.
Okay. I think the statement of universality of the subleading soft factor. A nice place to read about it is an old paper by, well, old now, I guess, by Henriette Elvang. There's only one operator that can correct it. It's phi r. If you have a scale, there's no operator that can correct it in pure gravity, but if you have a scalar, it can be corrected by phi r squared. The same statement in QED, it's correct. Well, in QED, it's actually corrected by, there's one correction, which is
axionic.
Psi bar gamma mu nu psi,
yeah,
mu nu and low already.
Realize that.
So it's universal in the fact that it doesn't get lots of random corrections, but there are a finite list of operators that correct it.
Very good. Thank you. Okay, good. Okay, so in the same way that there are these subleading corrections, people have understood that also they are related with symmetries for instance, in gravity. You see that well, David Nicholson was talking about this yesterday, that there are subleading corrections in the spatial part of the angular metric, and then you have here the shear, but then you have infinitely many other corrections. And these corrections, well, the work of all these people have been like try to understand how from these terms you can construct charges, and in general, the charges appear as the subleading components multiplied by a Smith parameter and then integrated over the sphere. Yeah, and this is how, at least at the level of the bulk, people have been able to compare and understand the role of these charges in relation with soft physics, and also to realize in the bulk these higher spin algebras, the W1 plus infinity in the case of gravity, and a similar one in Young-Mills. So in QED, there is also a similar story. Of course, it's simpler because the theory is abelian, there is an expansion in the 1 over r. So then you have this multipolar charges that are written here, Q0, Q1, Q2, and then you can also assign a type of charge. And here, well, there have been many works, but here I will be mostly focused in this idea of Campiglia and Lada in 2018, where they study those charges from the point of view of spatial infinity. So looking at the equations of motion close to spatial infinity, one is able to see some antipodal matching that gives rise to this type of charges. Yeah? I'm going to describe it here in the case of the scalar case. Okay, so also what I would like to understand, and probably in this talk I won't be able to do it, is that in which sense asymptotic symmetries at the conformal boundary of the space-time are really related to subleading subtheorems. And there is something that it's kind of telling, is that subleading factors, okay, are controlled by the frequency, by the energy, and then these enhanced symmetries appear in the 1 over r expansion. So as like Marius was saying, like at each order you get like a certain conservation loss. So then maybe one should start thinking again about like how to obtain these charges from or how to obtain charges that are related to these subleading subtheorems. So I would like to consider a simplest example, simplest setup, where I can try to start understanding this point. Okay, so the model I'm going to present is, I'm going to analyze the emission of a massless scalar at 3 level. So this is like a very nice picture taken from this paper by Duary and Ray, where you have an incoming set of massive particles that collide in a certain way, and then they go to future time like infinity. And in this process, there is an emission of one massless scalar. Yeah. So this is the main thing. What I want to do is like to study the amplitude associated to this process at the lowest order in perturbation theory, and see how this subexpansion arises as a tower of conservation loss. So the key idea, so then it's like analyze the subexpansion in scalar field theories from the action of these surface charges. So the question is like, why should I consider scalars? And it's because then I can really get rid of the gauge symmetry and see where, if there is such a charge that can be constructed in this analysis. Also because interactions have a well-defined soft-limit. So as Campiglia, Coito, Misera have shown, I mean, there is a soft theorem, and this is related to a certain conserved quantity. There are other papers by Marotta, and recently there is a more geometric viewpoint by Derda, Helset, and Parra Martinez. And I forgot also to put there a very nice paper by Biswas and Gordon Semenov, who is also like trying to understand like how the soft interactions don't decouple even in the way we understand it in electrodynamics, for instance. Okay, so here I will see that this emergence of the symmetry enhancement will come from the equations of motion close to spatial infinity, and this is what I would like to show. And then this will give me a systematic construction of these charges. So then let me start from functional infinity in a very similar way as Cresto and Freidel has been doing it, and also Celine did it as well. So it is necessary to consider the field components associated deeper in the bulk. So then if I have a scalar field that, okay, has this Fallov condition that is consistent with Lorentz symmetry, with Poincare symmetry, then I can define my charge as a sum, as a finite sum of coefficients in the asymptotic expansion times smearing parameters. And then I will demand, so this is defined at a certain sphere at a given time u. So then I can define those parameters, imposing that the fact that, that the time derivative with respect to u of this charge when news and external currents are absent, it's zero, then this allows me to fully determine this mu k coefficients. And in fact, here it will not be totally relevant, but you can find that those parameters have a power dependence in the retarded time. And then there will be a differential operator that I will show you a bit later, acting on a single function defined on the sphere. This is what you get from when you determine those coefficients. No, it's not obvious. It's not obvious. And you're totally right. This is the simplest set of boundary conditions. You can improve it, and you can add logarithms. And if time permits, at the end of the talk, I will show also like how logarithms arise in this context. Okay, good. So,
Another question. Is it clear that this determination can be uniquely performed, because you could still add anything to the charge, which is such that the dot of this is vanishing when there is no news?
so say again.
Is it clear that you can actually uniquely determine these mu's? Because it seems that you can still add to this charge anything such that when you evolve it, it gives a news. This would still satisfy the requirement that you're imposing. And indeed, in gravity, in this construction of Laurent and Cresto, it's really important to actually fix this ambiguity by some other requirement, which you can just get.
What I'm going to show in the next slide is like I can find the same type of conservation law from a spatial infinity. So that will give me like a clarity that this setup it's consistent with another one. So maybe it's not the unique way, but it's a one way that gives me an answer, the same answer in from two different viewpoints.
Okay, thanks. Another question.
If I understood correctly, you are making a choice for your boundary conditions, but you could maybe also do it in the way that Sang-Min was explaining it yesterday by choosing what kind of interactions you have, and then the boundary conditions for you are, you can derive them. There's no choice. You can derive them once you choose.
That's true. That's true. You can also do it that way.
Then either you will get logs or you won't get logs, so that will not be a choice.
Well, what happens here, maybe by chance, is that by using this branch of the solution of the boundary conditions, I get a very clear relation with polynomial expansion in the soft theorems. But then, of course, there is another branch that might give me other corrections. And yeah, of course, maybe there is another way of like seeing this problem from the point of view of, I don't know, interactions. Yeah, but since there are not so many, a scalar field does not have so many symmetries, it's more difficult to classify all types of interactions. So then maybe this is a bit, differs a little bit from the analysis that Sang-Min was showing yesterday.
Was another question?
I was wondering if you do something like this in a theory with Fisman, how you could give physics to these phi's, because there R would be just a coordinate. You could do any coordinate reparametrization, then the phi's will change arbitrarily. So in the gravitational case, how do you make sense of this?
I think this has been done, I have to check, but I quoted in a previous slide. I think this has been done by Compare, Serach, and Oliveri. The same type of analysis.
What has been, but
constructing the charge.
Coordinate dependent analysis.
Yeah, in Bondi gauge. Yeah.
Right, but then how do you give a physical meaning to these quantities, because they're not observables, right? And they're just written in one specific coordinate system, and you don't know what their geometrical meaning is, right?
Well, here I will show that even though they might be related to a certain specific gauge, they are somehow conserved. So then they have an interesting role in this game. So yeah, yeah, exactly.
But then you are also relating them to soft theorems.
Yeah,
after
exactly.
all,
That-
so in a
so-
sense.
yeah. So then the same idea, but from spatial infinity, same picture. And then the thing is that since I'm considering massive particles that are like departing from the past and going to the future, then they are really localized in the world lines of those particles. So then if I'm very close to spatial infinity, then I can, like, in a very good approximation, I can think of the dynamics of the system, of the massless particle, close to spatial infinity as a free dynamics. So then I can really study what is going on close to spatial infinity. So then this is like zooming in I0, and then this point is connecting the future null infinity with the past null infinity through hyperboloids. So then I'm using hyperboloid coordinates, and here I'm quoting the work by Fuentealba and Hernán, where they were studying this problem. And then if you consider reasonable falloff at I0, then the solution is determined by an extension of the Legendre polynomials, which are called the Gegenbauer polynomials. And then you can show that the solution is determined by one set of polynomials at scribe plus and another set of polynomials at scribe minus.
Excuse me.
Yes.
If are you considering the free case?
This is the free case.
Yes. Maybe I should say that long ago, Longhi Materassi, in the free case, they found an infinite set of BMS charge.
In the scalar case as well?
In the scalar case.
Ah, okay.
No, everywhere.
Okay, good. I mean, I will check it. Maybe later you can give me the reference. So then you can really see that if you go to, from above, you go to R going to infinity, and from below you go to R going to infinity, then there will be like a sort of equality between the polynomials, except for the fact that in one will be +1 and the other one will be -1. But thanks to the property of these polynomials, this will give rise to a certain matching conditions of the field. So if now I study the asymptotic expansion very, very close to this point, the field is almost the same as before, but now here I'm just saying that like it will be only dependence in X and no U. Dependence on U totally drops out when you study the equations of motion. Also, from below, you get a very similar field, but then the question remains if this phi f or phi p are the same or not. And thanks to the equation of connecting spatial infinity and these Gegenbauer polynomials, you can show that these two quantities are related, and are related not only by changing the sign of the angles, doing this antipodal map, by also like adding this -1 to the n factor that is very important for the derivation of the conservation laws. So then, in a way, these matching conditions really determine an infinite set of conservations parameterized by n.
The previous slide you mentioned reasonable fall-offs that are not.
Yes.
How do you define reasonable?
Like they go like 1/r.
So no logs at this moment.
Or could be logs, but like later in the expansion. The leading term has to go to like 1/r to spatial infinity.
Okay, but at Scry you don't consider any log terms, right?
Sorry, I'm not considering log at null infinity.
Yeah.
But like, sorry, I said it wrong. Reasonable boundary conditions at the spatial infinity, you will see that it will imply also logs. So here I'm just like removing one branch. Okay. So in the work of Fuentealba and Hernán, they show that if you impose reasonable falloff at I0, then you will see that there will be logs appearing in scribe plus and scribe minus.
Even when you don't have logs in at I
Even
naught.
when you don't have logs
Okay.
at the
Thank
scribe plus, scribe is 0. Mhm. Good. So then, if you impose a alternating parity, you can define two set of charges integral, and then because of the parity, well, first I have to say that this definition, and maybe this is related to Simone's question, this definition that might be coordinate dependent, it's really like you can really show that this combination becomes this other combination from spatial infinity when you properly do the expansion in phi and also in the coefficient mu. And you get exactly the same expression. So then these charges are conserved in that sense, in that like in the past of future null infinity and in the future of past null infinity, they are the same. So then even though those points are too close, they are infinitely far apart. So then this means that it's really like a conservation between the future and the past. And at the level of, I mean, then you can promote this condition at the quantum level, and as Strominger and many of people have been doing it, this you can use it as a symmetry of the S matrix. Okay, so I would like just to.
Yeah, quick question. Is there a physics intuition for this alternating parity condition?
Good question. Well, this is very similar to multipolar charges in electrodynamics. And then you observe this kind of alternating sign in this multipolar expansion. So maybe it's related to that. Yeah. So then what I'm going to do in the rest of the talk is like divide this charge into a soft piece and a hard piece, and then see what I get. Yeah. So here I felt like it was interesting to go case by case. So and put like the first 3 ones, the part related to the soft piece of the charge, and then you see that there is this parameter times du of phi 0, so the leading term in the expansion. And this is like the analog of the news in the scalar case, the derivative of the phi 0. And then you start seeing that there is an increasing power in u and a certain operator that it's the one that appears. This is the Laplacian on the sphere, and then you start seeing like more and more operators that are annihilating harmonics on the news. So then in the first one, you just annihilate the constant one, then L equal 1, L equals 0, L equal 1, L equals 0, L equal 1, L equal 2. So then this operator, so I'm defining it as this calligraphic BM, acts as a projector. So it's really like removing the first M harmonics from the news field. Yeah, good. And then you can really see that you can relate the soft piece of the amplitude of this commutator. You can relate it to an insertion of in this case, an annihilation operator, but then is multiplied by 2 things. First, by this operator omega dm omega that singles out the order omega m on this expansion in the energy. And then, of course, like since all the soft charges had this operator, this operator also appears here. Okay, but then the parameter f is chosen in such a way that you really are inserting a subleading soft operator. So this, in a way, I mean, using the language a little bit in a bit loose way, this is a universal piece in the sense that this soft will always give me an insertion of a subleading scalar. Okay. Then the hard piece is related to the source. So then I have to here think of like interactions with this field. Since I'm considering massless fields, you can parameterize, and this is also shown by Sang-Min yesterday. Like you can really parameterize this space-time with hyperboloids. So each tauical surface will be a Euclidean H3 space, and then the expansion of the current compatible with the asymptotic analysis start with 1/tau cube, and then you consider subleading powers. So then it's an integral over I plus. This guy is like the measure on the hyperbolic space. This is a parameter that I'm going to explain in a bit, and this is like the component of the current. So then you are really doing, so this, it's really related to the parameter that we found on Scribe Plus, but then it's projected onto future time lag infinity through this map. So in a way, here you apply this integral and you take this operator, you propagate it to the I plus. Okay, good. But one thing that remains to answer is like, we need to really understand if this is like really constructing soft subleading relations, is we need a model for this external current Jx. And here, I'm going to consider a toy model where I consider it's better to do it with complex scalar, massive, and with this type of sort of Yukawa-like interactions. But you need to handle this model with care because it has, so this is just to get an idea of the action of the charges. So I will present a 3-level computation, but it has to be regarded as an effective model because, of course, when you have massive scalars interacting with massless scalars, this Yukawa type of coupling, G is relevant, it's a relevant coupling. So then you might have problems if you study loop level because then G becomes it's like big in the infrared. So this is not a very good model. Also, phi is not protected by any symmetry. So there is no symmetry protecting the fact that under loop corrections, you are going to lose this masslessness of the field phi. Of course, from an effective point of view, you can always, at each ordering perturbation theory, you can add a counter term that annihilates the mass, but of course, this is not natural. But a better way of thinking of this model would be to consider, for instance, fields that have derivatives, because this will allow me to have a symmetry protecting the masslessness of the field. Okay, so going back to the hard piece. So now that I have a model, I can construct this hard quantity on the physical states of the process. And at leading order in G, well, first, I need to do an asymptotic expansion in 1/tau of the massive field. And then this is like done with the saddle point approximation, was done by Lada and Campiglia. And then the next, so this is like my size 0, the first order in its expansion, and then the rest are recursively determined by size 0. And what I get is that this hard piece start acting as a higher derivative action on the plane waves. So then in the beginning, this is a Schiff symmetry. This is the hard charge that already Campiglia, Misera, and Coito found. The action of the hard charge is like a shift, let's say. Then you start seeing like the first one acts as like a sort of diffeomorphism on the hyperboloid. And then you start getting higher derivatives that they might look like the higher spin analog of the action of these symmetries, but it's a bit different in the sense that you would like this operator to be, well, two derivatives and also traceless, that it's accomplished by this, but in this case, it's not like that. So then there are different things like comparing it with what happened in higher spin in 3 dimensions, for instance, because this hyperboloid is 3-dimensional, so then one could think that they are somehow related. Okay, so this is the action of the hard charge on plane waves. And then, to make the long story short, you really find that thanks to this projector, you can eliminate many terms that appear in this action, and you just end up with the one that is like this q times dq to the power m divided by this single pole that also appears in the leading soft theorem. Yeah. Is there any question? So then the question would be like, can we really get this result from the perturbative analysis? And the answer is yes. So then you need to consider like an insertion of a massless scalar at 3 levels. So there are 2 diagrams. Of course, this is the one that will be important. This will be subleading. I mean, it will be removed by this projector on the sphere. So then when you multiply by omega, and then you apply this derivative n times, and take omega going to 0, you have 2 contributions. One that looks pretty much like the one we have. It's a single pole, and it's also factorized. And then there is another term that is a power in Q. And the nice thing about that, and it was already noticed by Li, Lin, and Zhang, is that this product of Q's is like a representation of spherical harmonics. So then you can really annihilate it acting with many of those differential operators. Yeah. So this is what I'm going to do. And then if you use this identity, so this D acting on products of Q's. So yeah, the reason is like this Q is null. So then the first component is 1. Then the second one is normal vector on the sphere. So this is why the relation holds here. Using that, you show again that there is a 1-to-1 correspondence from what I showed from the charges. So that was the main idea I wanted to show, like how the charges are related to this perturbative result at 3 level, of course. So yeah, so these are our identities that come from a symmetry of the H matrix. Good. Yeah, let me give some comments that might be, enlightening for the future. So then we have shown that soft factors at order omega to the power m comes from inside in the bulk to the power r to the minus m. Of course, this is already known by people, but from a physical point of view, it's nice to see that, for instance, when one takes the saddle point approximation, and then you want to get the leading term in the field. So the real dimensionless parameter is not r, it's omega times r. So of course, like for very low frequencies, r going to infinity, it's really the asymptotic region. But when you really want to see what is going on at like a little bit bigger frequencies, so this analysis, of course, is very naive, but it tells you that you have to go somehow in the bulk. So the question that arises from this is that if you can define in a canonical analysis, in a canonical formalism, finite reduced charges. There are some directions where this has been fruitful. For instance, in this very nice article, like almost 10 years ago by Conde and Mao, where they were really obtaining charges in the 1/r expansion of the codimension 2 surface charges. And also like from what Celine was showing us yesterday, you can really consider finite charges in a specific, very specific case, which is the black hole horizon. So then this is more like a general comment. I don't have really an answer for this, but it maybe one might have to also try to understand these charges from the point of view of finite radius perspective. Okay, so I have a summary and I have something else. So if I have time, maybe I can also show it. I don't know if there are questions. I mean, I'm happy to answer as well. So there are infinitely many towers of symmetry connecting with this non-universal subleading sub-relation. So they are non-universal in this case because I have to choose the interaction. So the interaction is, I mean, depending on the interaction of the problem, then it's how I'm going to see the action of the hard charge. But of course, in any case, the funny part is that even though this is non-universal, you can really obtain, if you give me another interaction, I'm most certain that I will be able to obtain a charge that gives rise to this subleading relation. So in a way, these scalar theories offer like a more tractable way of understanding how these symmetries emerge. But also they have like some challenges that I want to talk a little bit. So of course, I haven't shown any Poisson bracket between these charges. Some stuff have been done in the case of two-form gauge fields. And I am quoting all these works by Campiglia, Friedel, Hofmüller, and Sony, Francia, Heisenberg, who did it like at the same time. And then Romoli also took this two-form gauge field and found very similar results to the one we found, but in the two-form gauge field. So in this dualizing the scalar field in terms of a gauge field. What is interesting is that if I regard the theory as free, close to I0, then we really know the bracket of the theory, and it's given by the Pauli-Jordan commutator. So in fact, two scalar fields at different points is just a C number. So it's given by a difference of propagators. So from that, you can really obtain the charges that, the algebra of the charges doing an expansion in 1/r of this commutator. Of course, this is a bit subtle and it's like subjected to regularization. So that's why I didn't present results in that regard. But in principle, you can do, from this bracket, you can extract the charges, the algebra of the charges. And also something that is nice, and I want to leave it as a comment, is that the theory is free, and then maybe you have to really consider not the symmetries of the Lagrangian, but symmetries of the equations of motions. And this very nice paper by Eastwood, where he shows that, I mean, the equations of motion has much more symmetries than the action principle. So probably, maybe, these symmetries are related to exactly the same idea. Okay? Well, there is this whole idea of loop corrections. I mean, the question is like, if these sub-theorems are protected by any symmetry, and in this case it's not, but there are models where you can protect the masslessness condition through a shift symmetry, and all Goldstone's bosons have this symmetry, and then you see that in this case you get, at leading order, you get the Adler zero theorem, so there is no soft pole. And then in this very recent paper, they have been also studying loop corrections in scalar theories. And well, they were mentioning that when you only have interactions through potentials, then it's unavoidable that you will have loop corrections of the leading software. But in any case, it's interesting, or like consider a more refined model where you can really study loop corrections and see if these symmetries that I'm describing today emerge in that case as well. And something that's been a work in progress, and Sucheta already asked me, is that in what I showed, I really like remove one branch, which is related to a logarithmic branch. So the question is like, what type of charges I'm getting from it? And maybe I'm gonna briefly comment, or maybe if there are questions.
See, maybe there are questions on this part. Otherwise, you still have time. But yeah, so you see.
Yeah, no, it's good. It's good.
So if you do a Fourier transform of all of these infinite tower of subleading soft relations, do you get like candidate memory effects, like an infinite tower of these? And do you have like physical interpretations for what they mean?
Yeah. I mean, maybe, yeah. Maybe they're related to tails in the waveform. Not exactly those, the ones I showed, but the one I'm going to present now with the logarithmic, they might be related to the tail of the waveform, and this is in some way a memory. But the ones I presented right now, I'm not quite sure how they can be related to memory effects.
Okay, thanks.
Just a curiosity, we know that in the case fields requiring gauge invariant can think about the conservation of a few groups.
Of the what?
In the case of gauge fields, requiring the gauge invariance of certain soft factors can tell us about conservation of a few global charges. Here you don't have gauge fields, but is there a version of?
Yeah. Since you don't have, you cannot apply that argument, but in a way, maybe it's related to the memory effect. I mean, you can maybe relate. Maybe it's like a sort of multipolar charge conservation. The zero mode. Maybe.
I'd like to come back to the the theory of Gaussian modes, which I think is very interesting. The theory is not free, even at I naught, right? Because it's a nonlinear theory. So have you thought about that? I mean, it would be actually more like in the gravity case, where gravity is nonlinear, and even at spatial infinity, you see that it organizes. I mean, there is a tower of fields. The leading one is free, and then the subleading one is satisfies a kind of free equation, but sourced by the leading field, and so on and so forth. So I suppose it would be a bit similar.
But maybe in some way it's also free in the sense that you don't have an external source in the subleading. It's related to some initial condition that I have to impose at the I0.
No, but here it's different because I mean the massless field itself, it interacts with itself.
Yeah.
There's no like free, part. And if you do, if the field, the massless field, has some fall off towards spatial infinity, at some point in the expansion, you will start to see these nonlinearities.
Yes.
It's just a comment, but I think it's to me it's really a more interesting case, but also
of course
more complicated.
Yeah, this is something that I also would like to see.
Yeah.
And like, I shouldn't say anything.
Okay. Thank you.
I'm wondering if you could just comment. Thank you for the nice talk. I wonder if there's also been some discussion of scalar fields that are dualizing the scalar field and writing it as the curl of a two form.
Yes.
And then you have a symmetry. And
wait a minute. So yeah, those three references they discuss they discuss that.
What is the relationship of that? Is it do you come to the same conclusion?
Yeah, exactly.
That way?
So you can really obtain these charges from the canonical point of view, but then you get these overleading gauge transformations that you need to regularize through the holographic renormalization. I mean, you just throw away this, or you add corner terms to the symplectic form, so that you eliminate these divergent pieces, and then you can really see in this work by Romoli, he showed that these charges that he gets from the two-form gauge field are really the ones we obtain. So there is this procedure there.
Hmm.
But I
The
would like to think
interactions
that-
that would be allowed would be different, right?
sorry?
The local interactions that would be allowed would be different, right?
Yeah, maybe it would be different in that case because I'm not sure if you can regularize them in that case.
Yeah.
Yeah.
Just to follow up on that question, Mark and Cedric also looked at two-form gauge fields and their symmetries at spatial infinity. So do you think there's a similar story?
Yeah, Mark told me that they were trying to understand this charge, but they didn't quite get exactly the same result as Campiglia and Coito-Misera. Yeah, this is the only thing I know. Yeah, but it's similar in a certain way. So maybe very briefly, I'm gonna just present something along the lines of extensions. Uf, ¿qué pasó? Ah, there you go. So then you can sort of generalize the boundary conditions that I showed. I mean, studying the equations with the logarithmic branch, you get another piece. But so then, this is kind of nice because standard boundary conditions on spatial infinity show that if you go to future and past null infinity, you get a logarithmic branch, but in a way it's nice because it's a single logarithm. You don't get like polylogarithm in the expansion if you allow for these standard boundary conditions are at I0. So then there is a new set of quantities, these psi quantities that I'm writing here, that are also subject to a different type of matching condition. And then like the parity now changes a little bit because there is an extra -1. And these parity conditions come from a second branch, which is the Gegenbauer polynomials of the second branch. And then these polynomials has only single logarithms. Yeah, good. So then again, doing the same story, choosing the parity of the parameter, I can define a charge. And that this one, I'm not sure if you can obtain it from the covariant phase space formalism. But then thanks to the matching condition, it's conserved. And then here there is two cases that are interesting. So the first two, m equals 0 and m equals 1. M equals 0 would be related to this psi 0 charge. And then this is the coefficient that is in front of the log r over r component of the gauge field, of the scalar field, sorry. And what is in a way nice is that it's totally conserved. So it doesn't depend on you. And since it doesn't depend on you, you cannot really obtain a soft theorem from this charge because you don't have like a flux balance equation. But in the next one, the m equal 1 case, which comes from this log r over r squared term. Yeah, log r. I need to point somewhere here. Log r over r squared term in the field. Then this charge, if you see what it gets, I mean, if you decompose it as a soft into soft and hard, then there is one term that looks, the soft piece looks a lot like what Sang-Min was showing, but except that this is the case for the scalar. So this is in fact a log omega insertion in the amplitude. And the hard piece that will be related to this part, this is what I was saying, is that this is like the tail of the field. So if you consider the news at future null infinity, then there is a component that is constant. I mean, it's only depends on the angles that will give rise to the leading scalar theorem. And then there will be an extra piece that is 1 over u, that is like the tail of this waveform. And this precisely match with the work of Duari and Ray, because this term is really what so in a way, what I'm gonna get here is that this term will insert a logarithmic term, and this other term will give me the tail of the waveform on the amplitude. So in a way, this is a very nice chart and a very nice extension of like the things I presented today. Okay, thank you.
Have you checked that the n+1 amplitude satisfy the at Pn expansion?
The which expansion?
I mean, you take the amplitude that you get and you go to the velocity 0, and you get connection with the Pn expansion. Have you checked that your amplitude satisfy the Pn expansion?
No, I haven't checked that, but it would be interesting to see.
I think that should be done to see if it's consistent.
Sure. I will.
Further questions? The last part? Yeah.
This is just a comment. There is another way of getting scalar charges from symmetry somehow. One way is to dualizing forms. Another way is from the double copy. So you get a double copy of two Maxwell vectors. The asymptotic symmetry of the Maxwell vectors in the double copy framework predict BMS super translations. And since the double copy field has a scalar in its belly, predicts the existence of these scalar charges and therefore.
Okay, very interesting.
Questions, comments? Okay, well, if not, let's thank Hernán again.